in this video, we talk about the Zeeman Effect, which is the last topic on the many electron atoms. So the Zeeman Effect, let's quickly talk about it. That is the splitting of spectral lines into several components in the presence of an external magnetic field. So remember that for a transition to occur, the energy that will be absorbed will be equivalent to the separation in the energy levels of the two different molecules. Okay, so if you have that transition going from the lower energy level to the upper energy level, you observe one line in your spectrum. However, in the presence of an external magnetic field, not just a magnetic field within the molecule, but an external magnetic field, a line is observed to be split. This one line is observed to be split into three. So that is what is called the Zeeman effect. So what causes it is because electron in itself has an inherent magnetic field, meaning that it behaves like a small magnetic dipole. Magnetism arises from moving charges, and since the electron orbits around the nucleus, so it has a magnetic dipole due to the orbital motion, so that's the one we refer to as the mu L. It also spins, so it has a magnetic dipole due to its spinning motion, and then when the two of them combine, then you have a magnetic dipole due to the total angular momentum as well. Generally, in the presence of an external magnetic field, a magnetic dipole has energy that is equal to minus mu B, where B is the magnetic field strength. So, in the lab frame, mu is a vector quantity that can point in the x, y, and z direction. So in the lab frame, we often consider z, and the magnetic component along the z direction is minus mu b jj mj, where mu b is called the Bohr magneton. It's a constant. G, this is a G factor. It characterizes magnetic moment of a particle or the nucleus of any particle that has magnetism. So this is Gj because we're considering the G factor for the total angular momentum. So we have the Gs and then the Gr as well. And then Mj, that's the and Mj is characterizes the direction of the total angular momentum J, much like M sub L characterizes the magnetic quantum number characterizes the direction of rotation for the orbital angular momentum. So if we put this in here, considering just the z direction, then the interaction energy is now given by mu b jj. So what does this mean? We recall that m sub j will have 2j plus 1. It takes values from j minus 1, so from minus j up to plus j. So if j equals half, so mem j can take minus half and half. If j equals 3 halves, then j can take values from 3 half, 1 half, minus half, and minus 3 halves. So in the absence of any magnetic field, all these levels, all this energy, these values are degenerate. They have the same energy. However, once B is turned on an external magnetic field, they are split into different energy levels. So we have the minus 3 over 2, minus half, all have several energy levels. And the splitting, the extent to which this is separated depends on the amount of magnetic field. So the higher the B, the higher the splitting. So this effect has been used to calculate or estimate the magnetic field of the sun. So this splitting is what we call the Zeeman effect. So it breaks the degeneracy with orbitals of same J or L or S in atomic energy levels due to the interaction between the magnetic moment of the atom with an external magnetic field. Like I said, the splitting is proportional to the strength of the applied field, and it is very small in magnitude. There are two types that is usually considered: the normal and the anomalous Zeeman effect. In a normal Zeeman effect, the splitting occurs when the state is between singlet, when the transition is between singlet states. So you're going from a state with S equal to 0 to S equal to 0. From the selection rule, delta S has to be 0. Because S is 0, J is therefore equal to L. And the energy of the magnetic dipole is now E equals mu B Jj M sub L B. So this becomes, recall in the previous slide we have ML but MJ, so it's now ML, which is associated with the total orbital quantum number. So this is a transition from a state with L equals to 1 and L equals to 2, where S is 0, so we are not considering S. So this is a normal Zeeman splitting. In the absence of magnetic field, so the transition is just 1 and one line is observed. So this Zeeman is often observed with a very accurate instrument. Okay, so according to the selection rule for transitions in many electron atoms, delta ML can take values, the change in ML values can be 0, plus or minus 1, and then L can change plus or minus 1 and 0 as well. That's for another video. Okay, so if ML can change by 0, plus or minus 1, so we have transitions that can go from 0, this is for plus 1, 0 to 1, minus 1. So when L is 2, we have ML can take values of 2, 1, 0, minus 1, and minus 2. And for L equals 1, ML equals 1, 0, and minus 1. So we have from 0 to 1, so that's delta ML plus 1, minus 1 to 0, minus 2, 2, minus 1. And we can also have from 1 to 1, 0 to 0, and minus 1 to minus 1, where delta ML is 0. And then from 2 to 1, so that's 1 minus 2, delta ML is minus 1. So 1 to 0 and 0 to minus 1. So that follows. So we can have three groups of transition. Delta ML equals 1, delta M sub L equals 0, and delta M sub L equals minus 1. So these lines, the separation between these lines corresponds to mu B, the Bohr magneton, times B. Because for this normal Zeeman effect, Gj is about 1, and M sub L, the separation between several lines, is 1. So this results to be 1. So this splitting, again, you call it the normal. This is a normal Zeeman effect. This is a Zeeman splitting. The splitting that we're talking about, so this is the 0, no field. So it's with respect to this no field. So we have the split in this direction and the split in that direction. Again, the splitting is small compared to the difference in energy of the states involved. Let's look at a quick example. Calculate the splitting in reciprocal centimeters between the three spectral lines of the transition between one S0 and one P110 in the presence of the magnetic field 2T. So 1, that tells us it's a normal Zeeman effect because the S is 0. So recall that E equals mu B, and that delta E is mu B times B. So this is given in reciprocal centimeters, this is energy in joules. So converting it, HC delta V equals delta E mu B. So we can calculate delta V by making it the subject of the formula. Substituting our values, mu B is a constant, B is given in the question 2T, H is a constant, and C is a constant. So notice here that this is 3 times 10 to power of 10 centimeter per second, because we are trying to get our answer in reciprocal centimeter. So we obtain 0.9. So let's quickly look at the anomalous Zeeman effect. The anomalous Zeeman effect occurs when the spin is not zero. The spin of the initial or final state, the spin of both of them, not just one of them, because delta S, selection rule delta S is equal to 0, is non-zero, and it is more common than the normal Zeeman effect. In the normal Zeeman effect, J equals to L. Here, J equals to L plus S. In the normal, because S is equal to 0, but here in the anomalous Zeeman effect, S is not equal to 0. And the splitting now depends on J, L, and S, not just, so it depends on L and S, and definitely J. So recall that each energy level is split into J plus 1. So the transition to S half to 2P half, it's not just dependent on S and P, it depends on the half, the S, that which is the S and the L. So the 2S half is split into plus half and minus half, 2P half is split into plus half and minus half, 2P 3 halves into 3 halves, 1 half, minus 1 half, and minus 3 halves. The energy splitting, the splitting or the shift to the position is still with respect to the energy of the magnetic field. And the energy interval in this case is now mu B into ml plus 2m sub s times b. So the normal Zeeman effect was called anomalous because the electron spin had not yet been discovered, and so there was no good explanation. So it is not because it is abnormal or because it's not normal, but because as at that point of its observation there was no good understanding of it. So this effect has actually been used to estimate the magnetic field of the sun. So a quick difference between anomalous and Zeeman effect. The normal effect is due to the interaction of the orbital angular momentum. Anomalous is due to orbital and implicit angular momentum. And these other ones are just additional explanation. This is observed at zero spin state. This is observed in the presence of an electron spin. The spectral line is split into triplets in the normal Zeeman effect. In the anomalous, it is split into complicated pattern depending on the value of L and S, the combination. So then, in the normal, it occurs in the presence of orbital angular momentum. So we mentioned that before. This one occurs due to both orbital and angular momentum. So those are the things that affect the spectral lines of many electron atoms. So we have the coupling of the orbital and angular momentum, and then we have other effects. There is another effect that can also affect it, the spark effect, which is an electrical analog of Zeeman effect. Okay. Alright, so we will stop